then basically, not only his time is wasted, used, and your time is also used. How effective that would be. What you want to do is, I'm spend one time saying I work on this document, I give it to him, and go away. Come back with my result. That is how you can scale. If you can do that, you can have so-called embarrassingly parallel system, right? You dish out work, they go and finish up. Typically, things are not that easy, so you do need to talk. That's why you're not have the 100% parallel execution. You have some communication overhead, right? That's why you have team meetings to sync up, basically, right? But your goal, okay? Your goal is to dish out the work as clean as possible, and that guy will never come back to you until they have a full result, ready to go, right? Some case that's too hard, then we have to basically have team meetings to get things straight. Okay? It's a balance between how big a chunk and how much time you spend. All right. So this is where we have operation-oriented design, data-oriented design. And eventually, we say, okay, guess what? They should be together. Actually, that's the rise of object-oriented design. All right. So these are the design activity. It's the same thing in classical design. Basically, that's when we don't have object-oriented languages. We only have C or Fortran, those kind of languages. We have to do classical design. That's architecture design, detailed design, design testing. Essentially, the input your specification and output is your module decomposition. In object-oriented design, the input is your specification, output your object-oriented design, module decomposition. Object, essentially your object description. Okay? Detailed design is module is actually designed. In that case, you are looking at algorithm and data structures. That is essentially the second half of our class, which is have you implement a class. Right? In first part of our class, we talk about how we partition. The second part is actually how we do it. How we do a module. That's how it's structured. Okay, in that case, you specify algorithm, you specify data structure. To give you an example, for instance, so I'm not very good at design, so I'm going to implement queue with stacks, right? So then there I only made stack data structure available to you, and you cannot use any other thing. So you have to come up with somehow clever algorithm to get that done, right? So that is actually what you did in that quiz is actually detailed design plus implementation plus testing. That is also what you guys have been learning on the 100 and 200 level. Okay? Detailed design by defining the data structure, picking the algorithm, get the algorithm implemented, tested. Okay? Once you get to 300 level, you partition the system into modules, classes. Then you can actually harvesting. You can harvest all the effort you have. You learned before how to implement the classes and assemble those things together into a running system, bigger system. Okay, that's it. All right. So this is the so-called operation-oriented design. This is still, you may say, oh, it's obsolete. No, is this not obsolete? You run any program, many of the program you run, command line program you run, no matter on Windows or on Unix or on Linux or Mac, you are still using this model, right? So here is a data flow. Basically, have input and output. Okay, is this also a state machine? Yes, it is. This is just a sequential state machine which never stops. It just go from beginning to end. And this also have a very nice name. A very nice name is this is also called a processing pipeline. If you ever heard about that concept, right? This is essentially your processing pipeline. What does pipeline mean? You pipe this data through a pipeline. If you have a pipeline, then you have the opportunity to parallelize things, right? When you put your first data in A, nothing to parallel. Once you move your data A to move to B stage, you can already put the second data in A stage. That is essentially data pipelining. Then at each cycle, at each stage, you can actually output. So if you run one input a time, that's the beauty of this structure. If you give it input, you say, oh, I would not give this guy an input until I see the output. How many stages will this guy take? I haven't counted. Yeah. How many stages? Say, if each stage take 1 second, how many seconds would this thing take to output the output? 8 seconds, easy, right? 8 stage, 1 second each. However, if I use pipelining, I put an input in this every second. How many seconds do I need to, how many seconds, so how many seconds do I need to wait to see the next output? 1 second, right? Once you push data into this, every second you have output. However, each job itself still takes 8 seconds. This is the beauty of pipeline. Your throughput is very high, but your latency is the same. Right? You still take 8 seconds travel from beginning to end. Right? However, you can actually have 8 things in the pipeline, so you will actually output 1 each. Oh, this is critical. You don't underestimate this single sequential line. Is actually critical in our system design. Okay. All right. So this is operation-oriented data flow analysis. You can see that this is with us ever since we have computer. This is the most popular model on computer, because at that time we don't have personal computer. Computer is really storage. The first computer as big as this room can do as little as this guy, right? So essentially that's how we do it. We take the input on paper, tape, or something like that, give it to the computer. Then we wait for like 24 hours and pick up the tape, right? This is the model. All right. So then you can. How do we implement this program? I mean, just like if you use Linux or anything like that, if you have something like, let's see, cat, right? The cat command, which basically shows the content of your text file, right? That thing is actually works this way. Okay. So how do we implement such a program? Well, this is how you're going to do it. You partition this into modules because you don't have the concept of objects. Okay. Before object-oriented concept got cooked up, there's no concept of object. So what do we have? We have the concept of module. In this case, you have your input module, your transfer module, and output module. This sounds so trivial now, but 60 years ago, 70 years ago, this is the state of art, and this is you can get a paper published by drawing this diagram. Right? So once knowledge becomes knowledge, then everybody knows. So it's not anything new. You have input module, point of highest abstraction. Then of input, you basically get that into something you can consume, process that information, and output that information. All right. So this is essentially decompose your product into 3 modules. Sounds familiar, right? This is basically decompose your system into objects. Same thing. Same thing. Repeat this until you, so essentially you partition this into something like this. Okay? This is your whole system. Right? This guy have 3 your main program, 3 modules. And also, you are assigning job responsibilities to the modules. Same thing as we did for objects. Same thing. Basically, what you are saying here is, this is what my system need to be doing. I'm going to partition my system into these things, and I gave the responsibility to them. Then I can give to you, so you can implement one module. Pure and simple. That's how we approach the thing. Divide and conquer. Divide and conquer. All the fast food restaurants work the same way. All the factory works the same way. Amazon warehouse works the same way. I mean, we didn't invent this ourselves. Actually, we learned from practice. You partition into modules, give modules to individuals, let them work on the module, and come back, we assemble the module together, we got the system. If your design is right. This is how we organize the team. This is also how you guys should organize your work, so you can scale from 200 line of code to 2,000 line of code. Same thing. You just treat yourself as a slave. Dish work to yourself as a slave master, essentially in that case, and say, do the job. Okay? That's it. Most of the time, because we are actually interfacing with ourselves, we don't write the documentation in a very detailed way, right? But once you really are going to interface with somebody else, you probably have to write that document sufficiently enough, so most of the time, your teammate can actually work independently. And only when something critically needs to be communicated, then you have meetings. If you are communicating, when the 8 hours he does his work, he needs you for 8 hours. What's the point? There's no gain benefit there, right? Then you don't have time to do your own work. All right, you can even refine into smaller modules because you're saying, this is too big a module for me to implement this one. I want 2 people to implement things, so I can get it done faster. Or I really want each module to be minimum, smaller, right? I can partition it even more. Again, we talked about this before. What should be your comfort level of partition? You can go this like all the way. I mean, so you can put, so I'm going to partition all the way to a single statement. Yeah, you can do that yourself. That's how you work. That's fine, right? But if you partition this to statement level, having her on your team doesn't make sense anymore, right? So she would be able to program this whole thing, and you gave her one statement that's basically too small to work on, right? You may just well give this big module to her to work on and take the responsibility, right? So it's all about how big a module your teammate can take. What's the unit of time to finish, right? Also, on the other hand is, if I gave this module to her, what's the likelihood of she will make a mistake, right? Everybody makes mistakes. If you give a smaller chunk, will minimize mistakes. Well, you may want to consider that. But too small the chunk, you will introduce communication a lot more. So it's a balance. So you actually want to, so if he can take care of 80 line of code worth of object, that will be where I'm going to partition my system too. 200 line of code, yeah, I'm going to give that to him to work on, right? If she's able to take 2,000, yeah, I'm going to stop there and let her take care of 2,000. That's how you scale. Same thing, I mean, you partition your system into comfortable sizes so you can work on yourself incrementally. That's how you should organize your own work, right? So the only way human being can deal with complexity is to divide and conquer. And how big a chunk should you divide it to? That you have to look at what's your comfort level and your team comfort level. For us, I think if your object really going down to linked list and tree, yeah, absolutely, that's enough. That's for us, that's absolutely enough. All right. Okay, so I'm going to continue. Because we are going to introduce pseudocode, which is critical concept and the tabular representation. So I'm going to stop here, and we'll keep up next time. So today we have another quiz coming up, which is, as I said, it's going to be a search. One thing I'm trying to do through the quiz is also help you to form a habit of having a basic code and adding to it. Okay? You need to grow your code base. You need to grow your own arsenal of libraries and code gradually. So you should have the ability to, for instance, start with something like a tray from last time, and being able to add to it here. So here I actually want you to add some functionality to your tray, so that you are, for any tray, any possible tray, using your existing tray data structure, I would like you to provide an interface function, also called method, to tell me how deep is your tray. Okay, make sense? So, in this case, if I have a tray like this, what is the depth of my tray?
Are we counting the edges or the vertices?
Edges or vertices, either way, same. What's the depth of this tray?
Because if we count the edges, then the depth is 2, but if we count vertices, then it's 3.
Yeah, so it's convertible, right? So that need to be so it's essentially there. If you count either way, you can count, right? So in the sense that you have your vertices will always be one bigger than the edge in terms of depth. Okay, so you can make that clear. Either interface would be acceptable. In this case, it's 2. How about something like this? How about this one? Let's count edges. 4. Okay. Something like that. 1, 2, 3, 4, 5. Okay? So no matter how complex the tray I gave you, you should be able to tell the maximum depth. Not a depth. This is one depth. You must count the maximum one. Okay? So this is actually the depth also is a search. All right, so this is here. The ideal case is you already have your trace data structure from last time. Now you're just adding one method to it, and you should easily be able to figure out the test case for this, right? First you create a tray, then you call this maximum depth method. It should return you the right number. Okay? That's how you should approach this problem. And here you are just adding one method. Nothing else changed.